Hello again, hackers. Last time we learned that text is not always just text. A name can bytes, bytes can become numbers, and if those numbers land in the wrong place, they can become control. But a basic overflow is only the beginning. It gives us the steering wheel. It does not tell us where to drive. In a return bin challenge, the answer is simple. Point the return address at a nice little win function, and the program does the rest for us. Today we take away the easy destination. No win function, no friendly flag function, no keen shortcut waiting in the binary. So instead of returning to one perfect function, we return from many imperfect fragments, tiny pieces of existing code, chained together by the stack. This is return-oriented programming. ROP shellcode brings its own instructions. ROP steals instructions the program already has. Before ROP makes sense, we need to slow down and look at the smallest moving part, the return instruction. When a function is called, the CPU stores a return address on the stack. That address means after this function is done, continue here. When the function finishes, red does not perform a ceremony. It does not ask whether the address is safe. It reads the top stack value, removes it, and copies it into EIP. That is the whole rule. Red trusts the stack. If the stack says return to main, it returns to main. If the stack says return somewhere strange, it still obeys. ROP lives inside that gap. The CPU follows valid rules, but the story those rules create is no longer the programmer's story. Our challenge is Pico CTF 2018. Can you get me? It is a good ROP lesson because the source is tiny, but the exploit is not just a single jump. A vulnerable function is almost comically small, a 16-byte buffer, a prompt, and gets. Get does not ask how big the destination is. It keeps copying input until the line ends. The buffer can be full, and get will still keep writing. So yes, there is still buffer overflow, but in this episode, the overflow is only the entrance. The real topic is what we put after the entrance. The first get address becomes the fake return address. After that, every red keeps asking the stack what comes next. At this point, the tempting plan is shellcode. Put machine code in the input, jump to the stack, and let the CPU execute our bytes. That plan depends on one assumption: the stack must be executable. If the CPU is allowed to fetch instructions from the stack, then data becomes code. But this binary has NX enabled, non-executable stack. The input can sit there as data, but the CPU cannot run it from there. So shellcode is blocked, but code execution is not impossible. NX does not say the CPU cannot execute anything, it says this memory region is not executable. The program's own instructions still live in executable memory, and if we can return into the right tiny instructions, NX has nothing to complain about. A gadget is a short sequence of existing instructions that ends in red, not because red is powerful by itself, but because red gives control back to our stack. Take pop EAX red. Pop EAX reads the next 4 bytes from the stack and puts them into EAX. Then red reads the next 4 bytes and jumps there. So every gadget has 2 effects. The obvious effect is the instruction, like changing EAX. The hidden effect is stack consumption. This is why the stack becomes a program, not because the stack is executed, but because the stack decides which executable fragment runs next and what data that fragment receives. Instead of writing assembly directly, we write a list of addresses and values. Red and pop interpret that list for us. Now we need the chain to do something useful. For this challenge, the classic goal is to ask Linux to run /bin/sh. On 32-bit Linux, a system call for int080 uses registers as arguments. EAX chooses the system call. EBX, ECX, and EDX hold the first 3 arguments. So our desired final state is precise. EAX must be 11. EBX must point to the string. ECX and EDX must be null. ROP is how we construct that state without writing new code. We need gadgets that load registers, gadgets that write memory, and one final gadget that triggers the syscall. The string /bin/ needs to exist somewhere in memory. EBX cannot point to an idea, it needs a real address. We choose a writable area like data or BSS. Then the chain writes a string there 4 bytes at a time. The double slash is not a typo. /bin/sh is 8 bytes, 2 clean 4-byte chunks, and Linux treats repeated slashes in a path normally. The first write is a tiny 3-step program. Put /bin into EAX. Put the writable address into EDX. Then store EAX into memory at EDX. First, ret enters pop EAX ret. Pop consumes the next stack slot. That slot is not an address. It is data for the gadget. Then the ret at the end of that gadget reads the next address. That address sends execution to pop EDX ret. Pop EDX consumes the writable address. Now EDX is not the string. EDX is the place where the string will be written. Finally, move bracket EDX, EAX writes the 4 bytes from EAX into the memory address stored inside EDX. That is the first chunk. Not glamorous, but extremely important. Most real ROP chains are made from small boring moves like this. Then we repeat the same pattern for the second chunk. EAX becomes /EX becomes /EDX becomes the writable address plus 4. And then we write 0 afterwards. C strings do not carry their length around. They end when a 0 byte appears. Now the string is real. It has an address. EBX can point to it. With the string prepared, the chain changes jobs. It stops writing memory and starts shaping the register state. EAX needs the syscall number, so we reuse the same kind of gadget, pop EAX ret followed by the value 0b. EBX needs the address of the file name string, not the bytes /bin/sys themselves, but the address where we wrote those bytes. ECX and EDX represent RV and NDEV-P. For this minimal chain, they can point to 0 or B0 depending on the gadgets we have. Sometimes a useful gadget sets several registers at once. That sounds convenient, but it means the stack must match the gadget's exact appetite. If we accidentally place the EBX value first, it goes into EDX. The CPU will not fix our meaning, it only follows order. This is the discipline of ROP. You're not only choosing gadgets, you're predicting how each gadget will consume the future stack. When the setup is finished, the CPU state matches the XXX syscall contract. The final address in the chain points to int 080. This is the moment where the prepared state becomes an operating system request. In 080 crosses from user mode into kernel mode, the kernel looks at EAX, sees system call 11, and interprets the other registers as execv arguments. And because EBX points at /bin/ the request becomes execute is program. The vulnerable program asked for a name, but the bytes we gave it were not a name. They were a return schedule. The stack was never executed. The stack simply kept answering the same question, where should we go next? That is a strange parallel of ROP and Xblocks injected code, but it cannot block the program from executing its own code. This is not read to win. Read to win is one fake return address pointing to one useful function. ROP is many fake return addresses mixed with values, each one moving the machine a little closer to the target state. Read to win asks, where is the useful function? ROP asks, what useful machine states can I assemble from the fragments available? So the stack stops being a place where functions remember the past and becomes a place where we describe the future. When programmers read code, we see functions, names, intentions, and structure. When the CPU runs code, it sees addresses, bytes, registers, and state transitions. ROP works because the machine view is lower level than the human story. If a byte sequence is executable and EIP points to it, the CPU will run it. The CPU is not confused. It is obeying perfectly the exploiters that rechange the data it obeys. That's why ROP is such an important idea. It separates code execution from code injection. So, the whole chain is this: overflow to control the first return, use gadgets from executable memory, build a register state, and finish with a syscall. shellcode says, let me bring my own instructions. ROP says, your binary already has enough instructions, I only need to choose the order. And the tiny instruction that makes the whole thing possible is RIB, one born instruction repeated until the stack becomes a program. Next time we can go one layer deeper, leaking libc, calculating base addresses, and returning into the share library every C program carries around. But for today, remember this, ROP is not putting code on the stack. ROP is using the stack to schedule code that already exists.